stand out? Physics? Any type of physics that you've seen that comes about in your daily life?
Push and pull.
The wind. It's cold.
Push and pull, that's a good point. Okay, the wind, okay. Right.
But I don't know, this week.
When did you do? Yeah, this is section number 3. You started September 29th.
Great day, Mr. Josh.
There you go.
Doing well, how about yourself? I was scared y'all were in some accidents last week or something with the storm or something.
No, I haven't worked. My schedule's changed, so gotta work it out.
My life went out though. It was out for a long time.
So
I don't got none now. Did you told her fun?
Oh, must be nice.
Don't worry about it. They can get you today.
Right. Today.
So we'll do module 2, working energy. Where is my
You better do Canada.
No, I'm trying to see. Oh, I haven't put it in. So problem set 4.
Oh, yeah, we don't have problem set 3. You know that, right?
Yeah, we don't have that.
They still got the eye thing turned off. So.
Yeah, I see.
And then we should see problem set number 4.
Yeah. You on October. Okay. So 3 wasn't. Okay. And then we're gonna have this one be due.
Yes, I do June 23rd.
So October 27th. So this should be the 20th. Problem set 3. Alright. Bless you. Alright, and then now I'll check. Exam 2 will probably be the 27th, I believe. Alright, so I'll check on that. The other thing I was about to do, to figure out attendance. Alright, cool. So So last time we were looking at 1 through 5. So I didn't get through. Well, I didn't go focus on the end of chapter 5 because it's not on our test. But just to give you guys a little preview, sometime later there may be some moments of using friction. So friction, we all know what friction is, but theoretically, something pushing away from us against our force of motion. But there's also static friction. So there's static friction and kinetic friction. So I just wanted to give you guys just a few little points.
Oh.
That's a weird sound.
Felix Baumgartner.
It's not cool.
I think it's loading.
See if it works on YouTube better.
So kinetic friction, is that like anything to do with like, I know kinetic, well, chemistry means like motion.
Right,
So
right.
that, I didn't know they go hand in hand.
Yeah, so friction, so kinetic is when two objects are in motion, and then statics, as if it is right now. Like there's still,
Energy to be created.
yeah, there's still some like micro forces that are at play that are keeping this from moving, or so that it's more difficult when it starts moving. Of course, like a smooth surface will have a lower static friction coefficient. So there's a coefficient that we use, a friction. Looks like this doesn't want to play very nicely.
History and conquered the skies by becoming the first person to break the sound barrier without vehicular power. Skydiving from a balloon a historic 39,068 meters above Earth's surface. He plummeted down, reaching estimated speeds of 1,360 kilometers per hour. Air drag is a resistant force that slows anything moving in Earth's atmosphere. When Felix is free falling, the force of gravity is constant and points downward toward the center of the Earth. Immediately upon jumping, this is the only force acting on him. At lower velocities, the effect of air drag can be ignored, but during high-speed phenomena, air drag must be included. Air drag always opposes the direction of motion. While the force of gravity is constant, air drag rapidly increases with velocity. If the velocity is large enough, the force of air drag will equal the force of gravity and cancel each other out. With no acceleration, Felix's velocity will remain constant from this point until his parachute opens. This is terminal velocity. Without understanding the fundamental physics behind the fall, Felix could easily have made mistakes and not survived the jump. Understanding the laws of physics makes seemingly impossible feats achievable.
Yeah.
I wonder how long that jump is.
Not 1,000 feet.
No, like, I mean, as
I
far
think
as
it's
time,
more.
like how long at the time?
10 minutes.
He broke the record for the longest, not free fall. Yeah, I think it was about 10 minutes.
That's not long at all.
That's long for a
That
free
is
fall.
long.
That's why I said 10 minutes.
That is
Like,
long.
why would you be free falling for 10 minutes? That's very long.
Really?
Yeah, this.
Like a free fall jump, like you go do it like for what's called, it shouldn't be no longer than like 30 or 45 seconds.
This is him right here. He's talking about Felix. He just said Felix. It was 128,000 feet up.
But you gotta think about it. Most free falls is just like you free falling off a cliff and just going straight down. Like how high
Okay, yeah, consider the speed too. Yeah.
4 minutes and 36 seconds.
That's it though. I mean, just to think that, you know, but then he could be at, you know, 500 or 700 miles an hour. You know.
To fall from that long, stratospheric jumps. Bomb gun, so he's near the stratopause. Here's a weather balloon.
But you fall faster. It's like not control. That's why people die. Because you're falling so fast.
The Burj Khalifa building right there. That's the highest building in Dubai. The tropopause before that, so Mount Everest is here. A typical airliner.
30,000 feet.
Okay, there we go. Some other type of plane. Ozone later, stratosphere. So they jumped. So first it says Kittinger, 1959 to 60, right here. And then Baumgartner, his trials. So this was the highest one he did, which was all the way up to a NASA satellite, a weather balloon. Is that a satellite?
Who did them other ones?
Weather
that little
balloon.
star and other square. What's what?
That would be Ustash. Ustash.
That's a different person.
Baumgartner has these three. Kittinger has these three. And then Ustash has this one.
He just got the one. He was like, that's enough.
Mm-hmm.
But his was the highest.
And this is the altitude in kilometers. So you said 30,000 feet. It's a little under 20,000 meters. The Aurora Borealis happens all the way up here.
Nobody
Thermosphere.
ever fell as high as the meteor.
Spaceship One. Cool. So that's something that I look at. Change in pressure with altitude gets lower. Altitude gets lower as you increase in altitude. And then temperature is weird. It goes low and then higher and then low again. It's like some convection laws that we look at as atmospheric scientists. Anyway, we got some friction. So kinetic friction, two surfaces in contact moving relative to one another, then the friction between them is called kinetic friction. Static friction can act between them when it's stationary, and static friction is usually greater than the kinetic friction between the surfaces. It's pretty interesting. So when the direction of motion is going that way, friction will be going to the left. So that's what that's saying. So that's the equation. When there is no motion between the objects, the magnitude of static friction is less than or equal to the coefficient mu s, static coefficient of static friction, mu.
What is it then? That's Newton's?
That's gonna be our normal force.
Oh.
Yeah. Do. So.
Yeah, lab today.
No, but we'll be able to get through some of the chapters. So when we do have time next week, when we are able to do our, I talked to him and he's coming. He's out of town, so I know that was one of the things that I wanted to do. But we'll be able to do that next week, weather permitting. We would have done it this past Thursday. But the weather had other plans. Alright, so find a small. So this is something, of course, we know what might happen. When you find a small plastic object, slide it on a kitchen table by giving it a gentle tap. Now spray water on the table, simulating a light shower of rain. What happens now when you give the object the same size tap? Now add a few drops of vegetable or olive oil on the surface of the water and get the same tap. What happens? This latter situation is particularly important for drivers to note, especially after a light rain shower. So that's the other question would be saying, when is the most dangerous part? When is the most dangerous time of driving out on the road? Yeah, when it's wet, and when it starts to rain, or when it's been raining for a long time.
Oh.
The landscape's a little more slippery.
But which one do you think though? When it starts to rain, or when it's raining for a longer period of time?
No, when it's raining for a long period of time.
When it starts to rain, because it's just like when you're mopping.
That's when it starts.
When you mopping the floors, if you just mop a little smaller section and somebody steps on it and you haven't got to the rest of the area, it's easier for them to slip. But if the whole floor is mopped, it's the same traction throughout the whole floor. So, and then people are more alert, but seeing it's like with the car, it's because the car is gonna follow up.
Yeah, so kind of like with your dirt or like little oils in the kitchen and stuff, when the oils mix with the water, then that's real dangerous. But then if it's been raining for a long time, then some of that oil gets to go away. So that's one of the reasons why that happens. And then that's talking about the ligaments, the bones, talking about friction in the bones.
In the body?
Well, I was wondering why we picture some skeleton up there.
Yeah, it has to do with the friction. It's artificial knee replacement is a procedure that has been performed for more than 20 years. In this figure, we see the post-op x-rays of the right knee joint replacement. But it's talking about these lubricants, like natural lubricants, slippery mucus found between organs in the body, allowing them to move freely past each other during heartbeats, during breathing, and when a person moves. Artificial lubricants are also common in hospitals and doctors' clinics. For example, when ultrasonic imaging is carried out, the gel that couples the transducer to the skin also serves to lubricate the surface between the transducer and the skin, thereby reducing the coefficient of friction between the two surfaces. This allows the transducer to move freely over the skin. So that's something, of course, our skier, again, normally we would have friction. So it's just talking about friction, the normal force. We talked about the normal force, the kinetic of friction equation with mu and then N, mu times N. So and then it's just asking what is the coefficient of friction. So that is, see, these are one of the things to think about this, Velcro would be a high static friction. Velcro should have a high static friction. So that's that. It's not too morning. So drag force, like we were seeing the skydiver, drag force, 1/2 the drag coefficient times rho. Rho has to do with the density of the fluid, A, the area of the object facing the fluid, and then V squared, the velocity. Yep. So one of the big things here that they pointed out is that A, the area. So if the skydivers, which one would be going faster? If a skydiver is going straight down like that, or if he opens his body and he's going down horizontally?
He's going straight down.
Yeah, going straight down. So that has to do that's directly related to this area, the area of the object facing the fluid. So if our area is greater, then we'll have a greater drag force. Much like when we drop certain objects, we talk about air resistance. So, in a frictionless environment and whatnot. So area is one of those things that would change your force of drag. All right. So that's one of the things. From racing cars to bobsled racers, aerodynamic shaping is crucial to achieving top speeds. Bobsleds are designed for speed. They are shaped like a bullet with tapered fins. And that's a wind tunnel. NASA researchers test a model plane in a wind tunnel. Yep, so the next thing pointed out, Michael Phelps. So this one's talking about these bodysuits. The LZR racer suit have been credited with many world records after their release in 2008. Smoother skin and more compression forces on a swimmer's body provide at least 10% less drag. Alright?
Yeah, that's why they shape your body.
Yeah, I've heard that. Alright, so that's gonna be that. Velocity, talking about drag force. Putting in the air density, an area of a skydiver, the drag coefficient, and then you get this velocity. This means a skydiver with a mass of 75 kilograms achieves a maximum terminal velocity of about 350 kilometers per hour while traveling in a head-first position, going straight down, minimizing the area and his drag. In a spread eagle position, that terminal velocity may decrease to about 200 kilometers per hour. As the area increases, this terminal velocity becomes much smaller after the parachute opens. Take-home experiment. Oh, I meant to grab these coffee filters. Maybe we can do that next time too. This interesting activity examines the effect of weight upon terminal velocity. Gather together some nested coffee filters, leaving them in their original shape. Measure the time it takes for 1, 2, 3, 4, and 5 nested filters to fall to the floor for the same height. Note that due to the way the filters are nested, drag is constant and only mass varies. They obtain terminal velocity quite quickly, so find this velocity as a function of mass. Plot the terminal velocity, v versus mass. Also plot v squared versus mass. Which of these relationships is more linear? What can you conclude from these graphs? So that's something cool. Might be able to look at, but I didn't really worry about it too much because it's not on our tests. And then this just talks about the viscosity of a fluid. Velocity, so it has to do with density and being able to move through. So that's the relationship with drag force. Stokes' law. And that's talking about the birds. Birds are aerodynamic, different animals. They have different ways that they can streamline their drag, and streamline their aerodynamics. So fish, dolphins, even massive whales are streamlined in shape to reduce drag forces. Birds are streamlined, and migratory species that fly large distances often have particular features such as long necks. Flocks of birds fly in the shape of a spearhead as the flock forms a streamlined pattern. And humans, one important example of streamlining is the, oh yeah, that's right. is the shape of sperm, which need to be efficient in their use of energy. So the birds are in this arrowhead shape, which apparently helps with drag, so that's why you see birds like that. Geese fly in a V formation during their long migratory travels. This shape reduces drag and energy consumption for individual birds and also allows them a better way to communicate. Galileo is said to have dropped two objects of different masses from the Tower of Pisa. He measured how long it took to reach the ground. Since stopwatches weren't readily available, how do you think he measured their fall time? If the objects were the same size but with different masses, what do you think he should have observed? Would this result be different if done on the moon?
I don't know. Well, there's no gravity on the moon, right?
Well, it's a sixth of our gravity on the Earth. So there's still gravity. It's just a sixth of it. So I would think that it would just be a sixth of, like, that it should still be pretty much the same. It's just that the time would be longer. It should be a sixth.
Oh, yeah. If it's more gravity, then it's going to
It'll just
drop rather.
faster.
Yeah, faster.
Yeah. This one kind of tripped me up though, since stopwatches weren't readily available. How do you think he measured their fall time?
That's a good question.
Yeah,
Just count it, I guess. Just,
that's what I was thinking.
When they have those things, the sand in it,
Oh yeah, that's a good point.
Maybe-
Hourglass.
Yeah, hourglass,
Yeah,
maybe.
that's a good point.
maybe they had a way of computing it by that.
Yeah, that would make sense. You can have the bigger hourglasses are maybe an hour, or it might be 5 hours or something. So yeah, that would make sense. That a smaller hourglass would just be 10 seconds, 30 seconds. So that's a good point. I didn't think about that. Right, just kind of
Knock it over.
yeah, that's a good point. So and then I was talking about Hooke's law, force of friction, the coefficient. K is a proportionality constant that depends on the shape and composition of the object and the direction of the force. So there's certain ways that, so this talks about deformation. A change in shape due to the application of a force is a deformation. So that talks about deformation, which is depending on the shape and composition of the object and the direction of the force. And then L is the force of function, the amount of deformation. So, and then we talk about when things break. So there's like a certain time when we can change some of our appearance, like some of the surface. If I push in, then I'm changing what my skin looks like when it's at rest, when it's at equilibrium or whatever. So it's elastic, it's changing, it's elastic. But and then there's deformation. So of course, like if I push harder and harder, I might cause a bruise or something.
And then something breaks, fracture.
Yeah, and then a fracture. So we can quantify this through physics. Graph of deformation versus applied force. The straight segment is the linear region where Hooke's law is obeyed. The slope of the straight region is 1/k. For larger forces, the graph is curved, but the deformation is still elastic. Delta L will return to 0 if the force is removed. Still greater forces